In my head, it rang this huge warning bell. It was like, this is like really weird. Like, this is not an argument that you would expect to appear in science. And when I looked into this notion of naturalness further, it turned out to basically be a beauty ideal. It's like we want our theories to be this way, but there is no further reason for it.
I'm Brandon Vaidyanathan, and this is Beauty at Work, a podcast about how beauty shapes our world and the work that we do. In this season, we're looking at beauty in science. This episode is sponsored by Templeton Religion Trust and the Institute for Advanced Catholic Studies at the University of Southern California. More about them later in the show. Hello and welcome. Thanks for joining us. I'm so delighted to welcome my guest today, who is someone I've deeply admired for more than 5 years now. Big fan of her work, Dr. Sabine Hossenfelder. She's a physicist, science communicator, author, musician, and YouTuber. She has published more than 80 research papers on topics ranging from quantum gravity to particle physics, cosmology, astrophysics, statistical mechanics, and quantum foundations. She's the author of 2 brilliant books, Lost in Math, How Beauty Leads Physics Astray, and then most recently, Existential Physics, A Scientist's Guide to Life's Biggest Questions. She's also the creative director of a super popular YouTube channel, Science Without the Gobbledygook. Sabine, thank you so much for joining us.
Hi, Brandon. Good to see you.
You too. Great. Let's talk about what drew you to physics in the first place. Could you talk about what influenced you as a child, perhaps, to move in the direction of math and physics?
Yeah, so I came to physics through the back door, so to speak. I originally studied mathematics, actually, not physics. And the reason I studied mathematics rather boringly was that, well, first, my mom was a high school teacher for mathematics and biology, not physics, biology.
Ah, okay.
And also, I was always good at math. And so it was the obvious thing to do. I would go and study math because, well, it seemed to be useful for something. I was also always interested in science fiction. And, I read a lot of books about additional dimensions, warp drives, hyperdrives, all that kind of thing, which I thought was really fascinating, which was all very math heavy. So that all makes sense to me. And then, after a couple of years, it came to this point where I had to pick a topic to write my diploma, as it was called at the time. I think now they call it a master's thesis or whatever. But that kind of level, after a couple of years, you have to make that decision, like, in which direction do you specialize? And I couldn't decide. It was like, everything is great. I loved it all. Differential equations, topology, higher algebra. I was super fascinated by higher algebra. Now I barely use it, but I thought it was great. And so I decided that the mathematics that I wanted to learn more about was that which described the real world, which naturally, directed me towards physics. And in addition to this, I had a math teacher who was at the time very interested in quantum gravity. So this was in the mid-90s when Ashtekar had just come up with what's now called Ashtekar's variables for the quantization of gravity. And this was a math professor, but he had a seminar on this. So by seminar, I mean it was like a semester, like half a year. And so I went to this. And for quite some time, I was under the impression that the problem of quantum gravity had been solved by way of these variables. And it took me some time to figure out that actually not everybody agreed with that. So, with that background, I accepted a position as a tutor in the physics department to teach mathematics to the physicists, the undergrad students. And, once I was there, they were like, you should make a diploma in physics. And here's your topic. and so
Okay.
this is how I became a physicist. But I think it's because of this reason that I've always had kind of an outsider perspective on the whole thing. I was more interested in what can you do with the mathematics? What kind of mathematics? Why this mathematics? Is there something that we can't describe by mathematics? Are there limits to it? And how does science work in the first place? So in hindsight, I think I might have been better off with the philosophers.
Okay. I mean, it seems like you were tuned early on to this idea of the unreasonable effectiveness of mathematics, right? As Winger puts it. I mean, what were your thoughts on that? I mean, about the ability of mathematics to describe things in the universe that maybe we don't need to know as humans, practically speaking.
Well, I've always found it weird how Wigner formulated the question, because I'd say, the parts that we call the natural sciences are those parts where mathematics works very well. So the statement is kind of tautologically true. I think the real question is more like, why is there some part of nature that can be described by mathematics to begin with? Like, the universe didn't have to be that way, so why is it so kind to us? To which I don't have an answer, I'm sorry, but that's how it is, basically.
Yeah. No, I've spoken to scientists and even mathematicians who are awestruck by this fact. Some of them prefer to just shut the door and say, I don't want to go there. I have no idea. And others, I think, have different responses. Some remain in a sense of wonder in the face of this and are convinced, therefore, that because we know so much through this particular language of God, as Galileo might put it, we should continue, right, really to invest in this and trust that it'll not lead us astray, which links to your book a little bit, which I'll ask you about in a minute. I did want to ask you a little bit about what your experience was like doing your doctoral and postdoctoral work, and in particular, as you talk about beauty in this book, were there things that were communicated to you as being beautiful, right, by your mentors, by your supervisors? Did they talk about certain ideas as being beautiful, or the importance of beauty as a heuristic? Did that come up at all in your formation?
It didn't, for the simple reason that the department where I made my PhD, it was nuclear physics. And nuclear physicists, they don't have a lot to do with this beauty stuff that you find among particle physicists and the other stuff that I ended up working on eventually. So what happened was I wrote, but I wasn't really interested in the nuclear physics stuff. It was mostly heavy ion physics, and it's very heavy on the numerical side, a lot of coding and so on. I don't mean to say that it's uninteresting per se. It just wasn't my thing because, as I said, I was more interested in this mathematical approach. So I was kind of an outsider in the institute in that I worked on some of those fundamental questions, in particular higher dimensional black holes. And at the time it worked because there was this idea that you could create at the LHC. It kind of half fit into the department, but not very well. And so after I'd finished my PhD, I wanted to properly get into the community that I kind of felt I belonged in, like this physics beyond the standard model. So I started going to conferences on supersymmetry, and I seminars on string theory, so on. And I moved to the United States, and with the intention of becoming a string theorist. This is actually what I said to my supervisor. It was basically the first day. It was like, "What brings you to the United States?" And I was like, "I want to become a string theorist."
Oh, wow. Okay.
And it didn't quite go as planned, because this is like when I was confronted with all this talk about elegance and beauty. And to me, it was really strange. It's not what I expected from scientists. And so I fell into this rabbit hole where I was trying to make sense of what was going on, which eventually led to my first book after 10 years or so.
Yeah, well, I would love to, if you could talk a little bit about that journey. Because part of it, I mean, when I probably came across formulations of string theory in a much more developed state, but it sounded a lot like science fiction. It sounded even a little bit like Tolkien. His, I don't know if you're familiar with The Lord of the Rings and the Silmarillion, and he's got this idea of the universe having been sung into existence, or, something of that sort, where their music is the basic sort of generative principle of reality. And it would seem, I suppose, appealing to someone who was an aficionado of science fiction to be drawn to something like string theory, I suppose. But you found it a little bit jarring, you say, with your expectations of how science ought to be conducted. Is that Is that right?
Yeah, but it wasn't string theory itself that I had a problem with. It was more the community. So here's an interesting factor that I think a lot of people don't fully appreciate, is that string theory actually came out of the nuclear physics community. It wasn't invented as a theory of everything, but it was actually originally intended to describe exactly the stuff that people at my department were doing, to describe the strong nuclear force, because you get those gluon flux tubes that are like strings. This is where it comes from. And this is still, it's now called the Lund string model after a city in Sweden where it was invented, but it's kind of a string model. So this is where it came from. And then they realized, through people who worked on nuclear physics, particle physics, like Veneziano, most famously, that this theory seemed to describe, how do I put this, a tensor mode, like a graviton, basically, like a spin 2 particle. And this spin 2 particle is believed to be the quantum of gravity. And in addition, the theory had some nice properties. And so naturally, at the time, this was like when the standard model was completed, so like in the mid-70s, roughly speaking, it was kind of the next thing that I wanted to do was to include gravity. And along comes this string theory, which seems to contain the graviton. So, of course, they were like, that's it. That's got to be it. And I think historically, this makes complete sense. And it also made sense to me. I've always, I found the idea very appealing. The devil's in the details, so to speak, because once you look at what can I actually do with it, problems start popping up. Like, at first they thought you need 26 dimensions, and then they added supersymmetry, and then it goes down to 11. And, then you have the problem with the vacua, and, other things, other problems with supersymmetry, and so on and so forth.
Yeah. Well, talk a little bit about then what led you to write the book, because you, in Lost in Math, and it's incredibly ambitious and incredibly bold, because you seem to be taking on certain kinds of orthodoxies around the importance of simplicity and elegance and naturalness, right? Could you talk a little bit about those three things and how those criteria for beauty have shaped physics?
Yeah. Before I do this, I want to tell you one more thing that maybe explains why I have this funny perspective on what's going on, is that when I studied mathematics, I had a boyfriend who also studied mathematics, but he had a second major, I think you would call it, which was sociology. So I became very interested in sociology, in particular in the question, like, what can mathematics tell us about sociology? So I've always had this side interest in, the dynamics of groups and what can go wrong in groups. Also partly, I think, because I'm German and, some things went wrong in Germany. So what happened was, after my PhD, as I said, I worked on the possibility that the Large Hadron Collider could produce those tiny black holes. And the first time I gave a talk at an international conference about this, so not an internal thing, someone asked me, why would those black holes be produced at the Large Hadron Collider? Why not at even higher energies? Like, why should they become accessible right now? And the answer I gave to this was what I'd read in all the papers. It's an idea called naturalness. It's because that's natural. And yes, you could push it to higher energies, but then it would no longer be natural. And this person, I still see him sitting there, nodded and was like, yes, okay. And I felt incredibly dumb because I didn't understand the answer. It was just something that I'd read somewhere. And so after this conference, I tried to make up for this and tried to figure out, like, just exactly how does this argument with the naturalness go. And now it's very interesting if you look in the literature, like, it goes back to an idea that came up in the early 90s or something around the time. People were very clear that this is an ambiguous concept. It relies on some arbitrary assumptions about the probability distribution, but it doesn't really matter. The thing is that it's a human construct, so to speak. And it fulfilled certain purposes, that which is why people invented it at the time, but it was never meant to be a criterion to single out particular theories as good and others as bad. This is something which developed much later, which indeed, interestingly enough, by Gian Giudice, who was, when I wrote the book, he was the head of the theory division at CERN, but I think he isn't anymore. In any case, so he's like a big guy in the theoretical physics community. He wrote a paper, which you can read on the archive, where he says that this idea of naturalness developed by a social trend or something in the community. Social trend is not exactly the phrase that he used, but it was something very similar. I'm not good with pulling quotes out of my memory, too old for this. Sure. And so in my head, this kind of, it rang this huge warning bell. It was like, this is like really weird. Like, this is not an argument that you would expect to appear in science. And when I looked into this notion of naturalness further, it turned out to basically be a beauty ideal. It's like, we want our theories to be this way, but there is no further reason for it. There are a lot of scientists, theoretical physicists, who have tried to come up with justifications for this idea, but they all fall apart if you look at them any closer. There have actually been some philosophers who've written about this. So I ended up in this weird position that, I had based my PhD thesis on something which, in hindsight, I don't think made any sense. So Do
you mean naturalness? Was naturalness per se part of what you assumed there? Okay.
This is the interesting thing. It didn't actually come up in great detail in my thesis. It's just, it enters in this assumption that it becomes accessible at the energies that the Large Hadron Collider could produce. So it underlies all those predictions for new physics at the Large Hadron Collider. They're all based on this idea of naturalness.
Maybe I should ask you to specify then before, sorry, just for our listeners who don't know what naturalness means, could you sort of give a brief definition of that?
Well, naturalness is the idea that if you write down a theory and you have to introduce some numbers without units, then those numbers should be approximately 1. Not exactly 1, but somewhere close to 1. And then we can discuss exactly how large or small can they be. Is 3 too large? Is 7 too large? Some people, would maybe accept even 10 or 100, but you wouldn't accept something like 10 to the 15. And the standard model happens to contain a number. Actually, there's a second number, but let's stick with one number that's best known, which is the mass of the Higgs boson divided by the Planck mass. That gives you a dimensionless number, which is about 10 to the minus 15. And physicists say that's too small. It's not natural. And so they think it requires an explanation. And this gives you justification to add all kinds of new physics. For example, supersymmetry. Or, for example, extra dimensions which lead to those tiny black holes. And there are lots of other things that you can add. They're all based on this idea that you somehow need to get rid of this small number. Now, there's nothing technically wrong with this number. It's just a number. You put it into the theory and it works. And that's, in fact, how people use the standard model. They just put in this number, done. So it's not like there's nothing wrong with it. It's just that they don't like it. And I didn't quite like this justification. And so what happened was, after my PhD thesis, I couldn't find a justification for what I had done myself. And no one seemed to understand what my problem was in the first place. People basically told me, I just don't understand undergrad physics. Look at those lecture notes, this kind of stuff. And so I was like, okay, I don't understand what those people say, but I want nothing to do with it either. So I decided I'd stop working on it. And that's what I did. Actually turned down a pretty big grant. And all my friends said I'm crazy for turning it down. But yeah, so I went to Perimeter and I worked at Perimeter Institute in Waterloo, Canada. And I worked on how to experimentally test quantum gravity for several years, because I thought it doesn't rely on this idea of naturalness. But this was all before the LHC turned on. And at this point, I was pretty convinced that all those arguments for new physics at the Large Hadron Collider were wrong, because they were all based on this idea of naturalness. So I started writing about it, first on my blog, started writing about this before the LHC turned on, I want to emphasize. Right. Well, you know how it went. Those new particles were never found. And after a few years of this, physicists began moving their predictions to higher energies, because that's the way the story has been going for several decades. And I just, it was just obvious that at some point they'd say, we need a bigger collider.
Right.
And this is when I thought I have to write a book so people understand that this argument isn't scientific. So we can discuss how well the broad public would actually understand what's a fairly philosophical, technical argument in my book. But still, I felt like I have to do it because who else would do it? Like I was basically the only one. And this is why I wrote my book. I just felt I had the responsibility to explain to people why, if they put all this money in a next bigger collider, it almost certainly wouldn't find something. And this almost is very important because, of course, I can't rule it out. It could always be, they find something after all.
Right. Yeah, so it's a sort of canary in a coal mine situation, right? It seems like you were sort of raising the warning bells and pointing to the red flags as the LHC is taking off. And so there's naturalness that's one of the criteria that's being used in making these predictions. There's also, you say, simplicity and elegance. Are they also driving these predictions? Could you say a bit about those?
Yeah, maybe one thing I should add is that the people who work on this stuff, they don't think of it as beauty. It's just, for the most part, they just use it as a mathematical requirement. And you have to prod them a little bit, to figure out just why do you use it, basically.
Because it's not necessary for mathematical consistency to assume these things,
exactly.
Right?
That's exactly the point. It's not necessary. And so besides this naturalness, they use simplicity, usually in form of unification. This is very prominently present in the idea of unification of the forces in the Standard Model, where physicists have developed new ideas starting in the 1980s, and they have been falsified to the extent that they could be falsified. There are still some, out there, which people are trying to falsify, and whenever one gets falsified, you can come up with a new one. So basically, it's not going anywhere. And then this idea of elegance is it's a fairly vague idea, but that people have quoted to me many times. It's basically this idea that a theory has to give rise to surprising connections. You have to get something out of simple assumptions. Yeah, for example, string theory is a theory which is often described as very elegant because it starts from this very simple idea. Everything is made of strings, tiny interacting strings, and they wiggle around and so on. But then you get out surprisingly many things, like, for example, the graviton, right? And you can also get fermions and bosons and gauge groups and stuff like this. So it's really amazing.
Yeah. But just because one set of theoretical assumptions can generate these outcomes, that doesn't mean there aren't other ones out there that may not look so beautiful, right? I mean, is that part of your argument there, that this doesn't have to be the only criteria by which we make predictions about theories, or that should drive theory choice?
Yes, it's a little bit more complicated. A lot of people think that I'm a string theory critic, which is actually not the case. As I said, I've always been very sympathetic to the idea of string theory because it solves a real problem, which is the problem of how to unify the Standard Model with gravity. So for which you need the theory of quantum gravity. At least this is the idea. Technically, it's never been shown that it actually solves the problem. So this is where the problem starts. I think string theorists have basically given up even trying. They generally believe that it does, but I think formally it's never been proved. So that's already weird. But at least in principle, I think string theory has a good motivation in the sense of solving an actual problem. So I don't have a huge problem with string theory, but where problems start is stuff like supersymmetry, which, string theory kind of needs supersymmetry, but let's leave this aside for a moment. Supersymmetry is believed to be necessary to solve this naturalness problem, but I'd say it's not necessary to solve the problem to begin with. So what do you need supersymmetry for? And supersymmetry is not just one model. It's a huge number of different types of models. It's really complicated, which is why there have been so many papers written about it, because there's so much stuff that you can explore in this great mathematical space. But as you correctly say, just because you can write it down and it looks pretty doesn't mean it actually describes reality. And there are lots of theories that you can write down that look good on paper, but they just don't describe the universe that we live in.
So is this massive sort of generation of papers around beautiful mathematics some kind of mathematical masturbation, or like what do you see as driving this kind of pursuit, right? I mean, I think one of the things you point out is just the abundance of papers that are being written, and even the abundance of journals. And I read some recent statistic that 70% of the publications these days in scientific journals are not read by anybody. And I wonder how this sort of the social context of science is driving some of what you're seeing here.
I think it's a generational thing. So I think that the people who originally started working on this, as I said, after the standard model was completed, they had pretty good motivations, and it made sense, that the next thing that you'd look at would be a grand unification or string theory, so you could include the graviton. But then over the course of time, this didn't work out, and people just started making those models more and more complicated. And it's around this time that things started going wrong. Then there were experiments coming in, and they falsified some of those theories, but they didn't get the message. They just continued doing the same thing over and over again. And then at some point, I think people learned that you can get away with it. You can do it. You can publish those papers, even though there's no evidence for it. And even if they are falsified, you just move on to the next thing, and that pays the rent. So it becomes this big bubble of nothing. And I think that they're not really aware of that this is what's going on, because if you've grown up in this community and I mean, they're all serious scientists, it's not like they're frauds or something. They all believe it. And it's really hard to go and say, well, actually, this doesn't make any sense. Why are you doing this? If you have like several thousand people telling you that, but of course, that's the thing to do. And this isn't something which is specific to particle physics. I find it interesting that a very similar thing has happened in psychology and parts of sociology, where they had this issue with the sloppy measures of statistical significance, which is something that mathematicians and statisticians have been writing and warning about for decades. It wasn't that it was difficult to realize. But they did it because everyone did it. It's what they, that's what they were taught to do. And they thought it was okay. So, and as I said, it becomes really difficult. If you are in this community, this is how you make your income. And it's okay because you can get it published, then you continue doing it. So so that's the interesting question, is then how do you stop something like this? And the psychologists manage to do it, right?
Right. Yeah. I mean, and they are still struggling with the reproducibility, replicability crisis and with p-hacking and so on. We still don't have enough respect for null findings. And so we were constantly chasing after whatever you can, demonstrate as being statistically significant, which is easy to manipulate. So, but I mean, these are really powerful biases that you point out, right? I mean, groupthink and social desirability and the sunk cost fallacy, and then this big blind spot that scientists of all people, would see themselves as being immune to these biases. So what was the reaction to your book? I mean, how did scientists respond to it? Were there people willing to say, gosh, I realized that this bias was driving me, or did they sort of reject your argument, or what's it been like?
There was basically no reaction from people in the community, at least not that I've heard. It's not that anyone came to me and said, oh, your book really made me think. It just didn't happen. But I mean, I've been very vocal about it, and I've made fun of particle physicists deliberately, I have to admit. And it's interesting if you look at interviews that particle physicists give on both sides, they don't talk about beauty anymore. This used to be really, really common, in public outreach, in popular science books, on all those pages. They would go on about how beautiful it is, and unification, string theory, and so on and so forth. They don't do this anymore. I think I reached some people. At least they seem to have realized that this isn't something that scientists should openly admit. Whether they actually stop doing it, that's another question entirely.
Yeah. I mean, there are, so on the one hand, so our data, when we studied, what scientists think about some of these statements, like, Dirac's claim that it's more important to have beauty in one's equations than to have them fit experiment. Most physicists would reject those sorts of claims, and most scientists seem quite circumspect and would say that beauty can be useful. It's fine to invest in a beautiful hypothesis, but don't be misled, like make sure that there's experimental validation and so on. But I mean, one problem, I suppose, is that regardless of what individual scientists think, it's the leaders in these communities that really, it's where the money is, or it's who's driving particular research programs, and they're the ones who get to decide really what you invest in. And so, and there are, it seems, prominent scientists. I mean, I'm thinking of people like Frank Wilczek, who I think is pretty outspoken about how beauty is a kind of, we can have insight into something like the mind of God, through the idea that nature embodies beautiful ideas, and we can access those ideas through mathematics, and therefore we should invest in this direction. I mean, what do you think of the influence of scientists who do have a strong sort of conviction about the role of beauty as a heuristic? Are you seeing that as still shaping the field, or do you think that's changed?
But as I said, I see less of it. Yes, there's Frank Wilczek. That's true. But if there's one person here or there, that's not the big problem. The problem is if you have a large group of people, and not only do they believe that beauty actually helps you discover new laws, but they also all use the same notion of beauty. And in addition, as I said previously, in many cases, they don't even think about it as some beauty. So if you ask them a question like, do you agree with Dirac on this quote, and so on and so forth, they put on their scientist hat, and most of them would say, no, you shouldn't do this as a good scientist. No, certainly not. Okay. But then they use some criterion like naturalness because they think it's just mathematics. That's what we have learned to do. So it doesn't trigger a warning, let me put it this way.
Yeah, so it's kind of baked into their processes, even if it's not sort of consciously being applied. I mean, and a lot of I want to ask about existential physics, which sort of resonates with some of these claims, where you're arguing that I think a lot of the kinds of questions that are being pursued in fields like theoretical physics are not even scientific questions, right? They're ascientific. Is that the right way? Is that how you put it? Like what kinds of questions are these, I suppose, that are driven by these kinds of beautiful mathematics?
I'd say it's not really the questions themselves that are ascientific, but more the ideas that people come up with to answer the questions, because they're just ideas that you can't test. For example, this is stuff like the existence of other universes is like a typical example. And I call them ascientific because it's not that they're wrong, but it's that science can't tell you whether it's right or wrong. It's not possible. It's like the idea of God, right? You can say, okay, God exists, but we can't observe him or her. And science just says, okay, so what? Do whatever you want. It's fine. It's not that it's wrong. We can't tell you whether it's wrong or right. And the idea of additional universes is one of that sort. This is maybe the most obvious one. I think most people would see that. But there are some which are a little bit less obvious. For example, there's like the question, what happened at the beginning of the universe or even before the Big Bang? Where I'd say, well, we can't tell because, first of all, we don't have the observations that date back long enough in the history of the universe, and it's highly questionable we'll ever have the data. And there are actually good reasons to think, just looking at the type of theory that we use, that it's actually impossible to go back beyond a certain point in time. And beyond that time in the past, you can do whatever you want, and it's not that it's wrong. It could be right, but we'll never know if it's right or wrong. And I would say that's ascientific.
Yeah, yeah. I mean, I recall, people like Jim Baggett talking about things like the multiverse theory as being, a fairy tale physics or something like that. I mean, that it's not even, or Peter White is saying this stuff is not even wrong. We don't even know what to call it. But is it a question that then this is not something that scientists should pursue, or is it that look, we're allocating public funding to various things, and particularly something like the Large Hadron Collider requires public investment. Is it a question of that, like, let's think about how we should direct our resources, and maybe there are other more pressing problems that we should be directing our resources to? Is that part of the concern here?
I have to admit that my concern with people who work on multiverse things is not very much about the funding, because it's very few people and they're not very expensive. Okay. It's not a big deal. My major issue with the multiverse is the same as Jim Baggett's, is that this public perception, as you say, like, this is not something that scientists should work on. Why do they do it anyway? Why do they think it's even science? There's something really going wrong. And because it's so obvious to see for people, I think it sheds a bad light on science in general. It's not that I have a problem with people working on it, but I think that they should be clearer that it's not science.
You're listening to Beauty at Work. This episode of the podcast is sponsored by Templeton Religion Trust as part of a grant on the aesthetic dimensions of science. Templeton Religion Trust supports projects as well as storytelling related to projects that seek to enrich the conversation about religion. To learn more about them, visit templetonreligiontrust.org. This episode is also sponsored by the Institute for Advanced Catholic Studies, a global research center located at the University of Southern California. IACS works to create dialogue, spark ideas, and sustain academic research on Catholic thought, creative imagination, and lived experience. Learn more at iacs.usc.edu. If you're enjoying the show so far, please subscribe to our podcast and take a moment to leave us a review. There's a lot of super interesting themes that you tackle in existential physics. Particularly this question of even life after death in the block universe. I wonder if you could comment on that, because there's the idea that we exist as information, and after death, potentially this information could be reconstructed at some point in the future is a really fascinating idea, and I think maybe a sign of hope for a lot of people. I don't know. What do you think of this particular idea, and what can science tell us about this?
So I don't think I said anything about whether it can be reconstructed, though I can see that people extrapolate to this. I think what I said is that for all we currently know about the laws of nature, the information that makes up you can't be destroyed. So it's still there. And yeah, God knows, maybe in the I don't know, 10 to 100 billion years or something, someone will figure out how to reconstruct you. I don't know. It's possible because the information can't get destroyed. And so there are two reasons I think that this is probably correct. The one is this weird block universe, the idea that all of space-time, not just space, but space and time, exists in the same way. So it's not just this present moment that exists, but actually all moments, they all have to exist in the same way. So this is a logical consequence of Einstein's theory of special and general relativity, which I think Einstein himself was very confused about, which is why he said he worries about this idea of the now, like where does it come from? Where I'd say, well, this is like some complicated neurological, I don't know what, it's not my discipline. So for what the mathematics of his theories is concerned, we live in this block universe where the future, the present, and the past exists in the same way. So then you have the possibility you can either say, well, nothing exists, basically, none of those times, or they all exist. And the other reason is the type of natural law that we deal with, which basically just tells you how matter is reconfigured. And it's a set of rules expressed by differential equations, and you can run them forwards and backwards. It's called time reversibility. And with two exceptions that I could talk about for several hours, which are black holes and the measurement process in quantum mechanics, all the laws of physics can be run forwards and backwards. And so this means basically that if you put all the information in one initial state, in one configuration at one time, you can calculate what happens at any later and also what happened at any earlier time. So this information is never really gone. does this mean that there's life after death? Well, it depends on what you mean by life, right? So if someone dies, then all this information spreads out throughout the universe, basically, and you can't communicate with the person anymore. So I'm afraid it's a very philosophical argument, but I actually believe it to be correct.
Yeah, yeah. No, I think, and it raises some really interesting questions as to how to think about, certainly the nature of time, and also I think it has implications for free will, right? I think your book raises some questions as to what science can tell us about the existence of free will, and I wonder, I mean, for a lot of people, existentially, free will has more to do with how much control I have over my own actions, how much responsibility, and typically that's the kind of context in which people think about it. How responsible should somebody be held to, right? So this is the question of justice and so forth, that, were my actions determined, or did I have some sort of free will? And so, but you're not dealing with it in that sense, it seems.
Well, so in my book, I do go on a little bit about moral responsibility because people always bring this up. It seems to be the point that philosophers are very, very concerned with. I find it to be a little bit of a red herring because I think you can reframe all those questions about moral responsibility in terms of interventions. Like, what are we going to do? Does it make sense to put this person into jail? Is it going to solve the problem? If it solves the problem, then the person was responsible. If putting them in jail doesn't make any difference, then maybe somebody else or something else was responsible for it. So it becomes a question of inferring the most dominant causes that created a certain situation, something like this. And I know this all sounds very technical and abstract, and I don't want to tell anyone that this is the language they need to use. If they want to continue talking about free will and moral responsibility, this is all fine. I'm just saying you don't really need it. If you wanted to, you could come to the same conclusions without it. And you're right. So this approach to free will, talking about how free am I from constraints in my environment? How autonomous can I make my decisions, or do I just act, like a toaster? Someone switches a button and you go bloop. This is not how we think about ourselves. So there are different ways that people have tried to give meaning to this notion of free will.
Yeah, and I think it has a lot of interesting relationships to philosophical positions where, autonomy or responsibility in some positions is really what makes us human. And, so if you take that away, that ability to sort of control one's own destiny, then that entire sort of philosophy starts to lose its appeal. And so I think people might be concerned about those sorts of things. But I'm curious to know as to whether you've yourself done anything differently, I suppose, in your life as a result of thinking through these issues, or as your own scientific research has progressed. Have you changed anything existentially, let's say, about your own life?
Yes, I actually have, both regarding the first book and the second book. So maybe let's start with this question of free will, because we were just talking about it. So I think that this idea of free will, which I think people are tied to it just because they've grown up with it, it's how we've been explained, our brain works, and it's very strongly anchored, especially in Christian religion. It's really important, this free will thing. So I think it suggests to us that we have more influence on what goes on in our own brain than it's actually the case. And I think the realization that free will doesn't actually exist, at least that's what I would say, has made me more aware of being really careful with what kind of information I let into my brain in the first place, because I can't get it back out again. Once it's in. And this has a lot to do with, filtering the information that you consume in a day. And it also ties into this question with the cognitive biases. There's just the human brain works in a certain way. If there's something that you hear repeatedly from people who you trust, you're very likely to believe it. And I think this drives a lot of this stuff in the physics community. And it's also why I thought eventually I have to go and come out with my first book, because I felt like I was subject to exactly the same environment, and I should not agree with them just because so many people say it. And from the first book, the lesson that I've drawn is basically about the way that I pick my own research topics. So I try to actually walk the talk.
Right. That's great. You have a really beautiful quotation that struck me about science communication and in your second book. And you say that alongside public lectures, we should offer opportunities for lecture attendees to get to know one another. And instead of panel discussions among prominent scientists, we should talk more about how scientific understanding made a difference for non-experts. Instead of letting researchers answer audience questions, we should listen and learn from those who have been helped through difficult times by scientific insights. Clear View of the Night Sky, a book on embryology, an online course in psychology, all this sort of stuff. I mean, so I would love to hear your thoughts on what might better science communication look like, particularly in light of what you just talked about, these different sources of information we're getting. We seem to be, at least in America, living in silos where we're conditioned only by, certain kinds of channels of information. So I'd love to hear your thoughts on what can break us out of those silos and what role science could play in helping build solidarity.
It's funny you'd mention the United States, because I actually think that science communication in the United States works much better than it does in Germany.
Oh, wow. Okay.
Because, at least you have some support for it. And I think politicians and a big part of the public understand how important it is. So in Germany, it's really, really difficult to get support to do anything in science communication. Like, I've never been paid to work in science communication. And last time I looked, the only support that you could get was to communicate your own research, which, is better than nothing. But it's not always a good idea to let the people who work on the stuff advertise it, if you see what I mean. Right. So what can we do better? I think there's good stuff going on, but it's not a lot of it. For example, one community who's doing really well integrating with the interested public are astronomers, with observatories. They tend to have regular meetings. Everyone has the telescope, looks at the night sky, they try to take pictures. They talk about the pictures, It's a very social thing. And I think that's great. And I think that other areas of science could try to learn something from it. Okay, not everyone's going to build their own particle collider in their backyard, kind of thing. But, I think we could do... What you see in a lot of science communication is that you have this very strong division between the person who's lecturing and then there's the audience, right? And I think we could try to integrate a little better, make this a little bit more social, to not give people the idea that we're talking down to them.
Yeah, no, I think that's really crucial. In fact, one of the main motivators for our research on this project on beauty and science was to figure out whether better emphasizing what scientists found beautiful in their work. And I don't mean just sort of those narrow, rigid types of beauty, but also the beauty of the stars and the beauty of phenomena they study, but especially the beauty of understanding. We wondered whether that could help. A lot of scientists told us we were being naive, and they thought that scientific facts, no matter how beautiful, will only be filtered through people's political priors. But our question is maybe it's not the beauty of facts, but rather the beauty of understanding. And I think your book points to the centrality of understanding. That ability to gain an insight into how reality works, even in a small way, requires some kind of intellectual humility. You have to be willing to change your mind. You have to perhaps even be able to find changing your mind pleasurable. And I wonder how we might cultivate that kind of sensibility, that kind of beauty of understanding.
Well, yeah, that's a very good point. I think it comes back to this social acceptance, basically. I think when, in many cases, you see this on social media a lot, when people change their mind, they kind of feel like they're getting punished, right? Because people make jokes of them. Like, hey, 2 years ago, you said something else, right? Look, here's your tweet from, and so on. And I think that's really bad. Personally, I'm glad if I see a politician change their mind, because it tells me that they can integrate new evidence. They've learned something new. So I hope that maybe we can try to change this mindset a little bit to make people feel more comfortable by telling them, okay, if you change your mind, that's great. That's exactly what you should do if you learn something new. And I also think a lot of people who, deny that climate change is caused by humans, who are still around, it's probably, this is my suspicion, is because 30 years ago, that was still kind of compatible with evidence. It was an acceptable position to hold, and they missed the bus. They didn't jump off at the point where they should have. And now they're kind of locked in this position where they feel like they would embarrass themselves if they admit they'd been wrong.
Yeah. You've done really extraordinary work with science communication, and I think at the end of the book you talk about how you came to the same conclusion as your mother about the meaning of life. Could you talk about your own sense of meaning and mission in relation to science, and how that shapes what you do now and what you hope to do next?
Yeah, this another very good question, because it returns us to the beginning, which is a very nice way to end. Yeah, so as I said, my mom is a now retired high school teacher, and so she told me that her idea of the meaning of life is to pass on knowledge. And as you can see, I kind of do the same thing. I didn't want to become a teacher because I didn't want to do the same thing that my mom did, but I'm also passing on knowledge. And you started asking about this question, like about the unreasonable effectiveness of mathematics and the natural sciences. And I think one of the reasons, and this is like pure speculation, is that our brains are kind of capable of forming a model of the universe. Because this is what it means that we are able to do science, that we are able to extract these abstract patterns, this mathematics from our observations. It's because it maps to something in our brain. We can deal with this. So in some sense, we're kind of similar to the universe, which brings up the question like, why? And where is it going? And so I've been wondering if not where the universe is going to. We kind of know that complexity is increasing, is trying to better understand what itself is doing through us. So in some sense, I'm part of the attempt of the universe trying to understand itself.
Yeah, that's beautiful. It's a very spiritual way of phrasing it, right? So we are the universe's self-consciousness as it moves forward. And yeah, lots of brilliant parallels, intersections between science and religion and spirituality in your book. And where can we direct readers to in terms of the work you're doing? Where can we direct our listeners, our viewers, our readers?
It's very easy. You just enter my name in your search engine of choice, and you'll learn more about me than you ever wanted to know. My name is not very common, so it's really not hard to find.
Fantastic. All right. Well, we'll put all the links in our show notes. And what's next for you? Are you working on another book? I know your channel is brilliant, and I really enjoy watching your news feeds, your analysis of all the science news. But what's your next project, if there's a big one on the horizon?
Well, I'm still working on trying to solve the measurement problem in quantum mechanics. So I hope that in the next time I'll be able to spend a little more time on this again, or doing a little bit more research again.
Okay, wonderful. Well, thank you again so much for joining us. It's been such a pleasure.
Good to talk to you.
Hey, everyone. Thanks for listening to this episode of Beauty at Work. Please be sure to check out our show notes for more resources from our guest. And if you like this episode, please be sure to share it with your friends. And please leave us an honest review. We'd love to hear what you think, and it helps to get the word out about our show. Music for the show was provided by Venkat Subramaniam, and the podcast was edited by Dave Visaya from Podcast Engineers. And thanks again to our two sponsors, Templeton Religion Trust and the Institute for Advanced Catholic Studies at the University of Southern California. To learn more about our research project on beauty and science, visit wellbeinginscience.com. To learn more about our broader project on beauty at work, visit beautyatwork.net. Thanks again, and see you next time.